Today we will be learning about the ideal gas law. The ideal gas law is made up of the equation PV equals nRT. P is pressure, and we're going to measure that in ATM. V is volume, and we measure that in liters. N is moles, we measure that in mole. R is the gas constant, and T is the temperature, which we measure in Kelvin. And the gas constant is 0.0821 for ATM. This equation assumes that there are no IMFs and there's no volume to take up more space. A quick little practice problem to use for this is finding the pressure of, say, 4 moles of H2 in a 292 Kelvin solution in 2 liters. So what's the pressure? Well, if we put into the equation, we have PV equals nRT, and that's 4 moles of H2 in 0.0821 because it's ATM, and 292 Kelvin, and the volume is 2. So if we divide it all by 2, then we can get the answer, which would be 47.95 ATM. Just kidding, go. So what we want to learn about the ideal gas law is what deviates more. And deviations in the ideal gas law are based on a lower temperature, because that means that there's less energy to break the IMFs. So that makes the IMF strength seem stronger, and a higher pressure, because that means that there is that the molecules are closer, which also means that the IMF strength is higher. For certain other molecules or atoms, if the increase of size, if there's an increase of size, then that means that there is a lower volume, and that would mean a higher pressure, and that goes directly back there. What about volume? Well, for volume, we can have one tank be no volume or negligible, and one can have volume. And for the one with no volume, there's really small little particles or atoms, and they don't really take up any room, so that's almost negligible. But with volume, got these big honkin' molecules, and that means that it is, first off, less empty, and there is a decrease in volume, which is because of the increase in size, and there is less entropy. And by that we mean there's less places for it to be here than here, because it can be all over here, there, there. But here it's just got, because it doesn't have as much room, it can only go so many places. What about IMFs? Well, with IMFs, we can have this tank be without and this tank be with. So without IMFs, we have these atoms bouncing off the walls. It's really random. They're lonely. They don't have anyone. But with IMFs, they've got the buddy system going on. And they go off in whatever their IMFs are. So because they have this connection, it is not as random, and it doesn't hit the containers as much. I spelled doesn't wrong. And because it's an increase in IMF strength, it is a decrease in pressure. So here's a practice problem you can try on your own. And it's going to ask what deviates most or least out of the given chemicals. So we can have H2, O2, xenon, or H2O. So you can pause the video and figure this out and then unpause it when you want the answer. So the answer is, for most deviation, you're going to have H2O because it's polar, and the polar property makes the IMF stronger, which makes the molecules stick together more, so they bounce off the sides less, lowering the pressure. For least deviation, or most like an ideal gas, it's H2 because it has the weakest IMFs, which is London dispersion, and it's the smallest in size. So thanks for watching.